Hi, everybody. I'm Albert Gnadt. I'm a postdoc at MIT. I'm in the Julia Lab. And
I'm Alan Wollaber, technical staff member at MIT Lincoln Laboratory.
Great. And we're here today to talk about knowledge-informed learning in MagNav.jl for magnetic navigation. And in general, we're going to introduce you to magnetic navigation if you haven't had any background in it. And so we're part of a larger team that works on this project. And it's a collaboration between the Air Force, MIT, and Lincoln Lab. So you can see me in the middle with MIT Julia Lab, and you can see Alan with Lincoln Lab on the right side.
Jonathan's in the audience.
Oh yeah, we have Jonathan as well from Lincoln Lab. He's one of the co-PIs on the Lincoln side. And just to introduce you a little bit to the actual problem. So what we're looking at is magnetic navigation. And so the general idea is that the aircraft is flying somewhere and the initial position is known from probably GPS, but then that signal is lost and you're not able to navigate anymore, but you still have an INS system on your aircraft, so you have an inertial solution to where you are. But that INS drifts over time, and so we can correct the INS using magnetic measurements, and you basically compare some measurements from the aircraft to some known magnetic anomaly map, and we're going to dive in a little bit more into these maps in the following slides, so don't worry about what that is right now. And just to introduce you to what we're specifically trying to solve with this problem, the signal that's actually measured isn't just the magnetic anomaly field, the thing we care about. It actually contains multiple components. The first one is the core field. That's what your compass would really measure. It's the very large scale signal. Then there's temporal variations, also known as space weather, and that's different smaller magnitude signals going on in the ionosphere. Then there's the anomaly field, and that's what we care about. That's basically the crustal field of the Earth, like the rock bed, that type of thing. Then there's one other signal in your measurement, and that's your platform effects. Basically, the aircraft has its own signal, and it's treated as noise. And for different aircraft, that noise is a different magnitude. So for a geosurvey aircraft, we'll see an image of that in a following slide. They basically measure out the back of the aircraft on a boom, and it has very low noise because you're so far away from all of the different equipment. But on a fighter jet, it's a little bit different. You can't really put a boom on a fighter jet, and so you have to try to measure somewhere in the aircraft, and there's extremely high noise. And so that's the problem we're really trying to solve eventually. And just to give you an idea of the kind of overall steps for doing this type of navigation, there's some sort of sensors, the INS system, like I mentioned before, magnetometers that measures your magnetic field, and you have other sensors as well, barometer, that type of thing. You get these different readings, and you need to compensate the magnetic signal. That's the real challenge, to remove these platform effects, we call it, or the noise in the magnetic signal. And those signals go into the navigation algorithm along with some magnetic anomaly map. And the state-of-the-art model is a linear model that uses basically two different magnetometers, a scalar measurement and a vector measurement. And then there's this linear correction term. We're not going to worry too much about these coefficients. They're Toles-Lawson coefficients that are found using a special calibration maneuver that's done ahead of time. But long story short, it's a very simple linear model that's been used since the 1950s, and more or less we're trying to improve on that. And so just to kind of summarize the problem here, this is a geosurvey aircraft. This is how the measurements are currently done by geosurvey companies, and they measure out the back using a tail stinger, they call it, or it's basically a boom. That type of system is not realistic in operation. And so what we want to do is measure somewhere in the aircraft with these temporally corrupted measurements. And so we're doing all this work in a package called MagNav.jl, and this is open source. We'll dive into a little bit more in the following slides. But at a high level, it has basically 4 different type of areas. The first thing is you can load in or simulate different magnetic data or INS data. And there's a bunch of open source data that automatically is downloaded with artifacts. And then there's also a bunch of map functions, a ton of map functionality to generate that map like we saw before. And we're going to actually demo that later on. And then there's different compensation models, which are used to clean up that magnetic signal. And then finally, there's different navigation algorithms. And just a few months ago, we released version 1.0. So the code's pretty stable now. We're actually on version 1.1 as of a couple days ago. And it's not currently registered, but it should be, I think actually tomorrow. There's a 3-day waiting period we didn't know about. It was supposed to be registered for this talk, but very soon you can just do add MagNav and it'll just work. We have all the things you'd want per package. We have a little API, and you can see our symbol in the upper left. I designed that. And then we have a Docker that you can use if you just want a quick start and not have to worry about installing all these different packages and whatnot. We also have a custom flight data set. Like I said, it automatically gets downloaded with the package via artifacts. So most people don't have their hands on any real data, and we have a very custom, nice data set that was generated for this project, this larger effort. And then more recently, in the past few months, we've added some new capabilities to the package that are designed to move towards using it in real life, using it in operation for like the Air Force or that type of thing. And so we added a navigation filter that has real-time capability, so you can take in one measurement at a time, figure out where you are, take the next measurement, et cetera. We also have 3D flight capability. For development, it's a lot easier to use a 2D map, but if you're out in the real world flying around, you're in 3D. And then finally, we have different functions for combining maps and plotting maps and that type of stuff, and we're going to demo that later. It's kind of cool. And then Alan, actually I have one more slide I forgot I added, just because it's relevant for the demo later on. So to generate these maps, it's kind of interesting. They fly around with that geosurvey aircraft, and they're on this thing called the drape. Basically, they're trying to go as close to the ground as reasonable. And then if you actually want to generate a map, you do this process called upward continuation. So if you want to map at this blue level, you just upward continue the map. You take all these values, you move them upward to the blue line. But if you want to map at a lower altitude, you do the upward continuation for a lot of the points, but in some cases you do downward continuation. And that's actually very unstable. The noise kind of expands, or it grows if you do this downward continuation, because it uses some Fourier transforms, that type of stuff. And so in general, you want to only do upward continuation. But yeah, I'm just giving a little background because we're going to show something related to this later on. All right, Alan.
Okay. And now onto the knowledge-informed part of the talk there. So what's interesting about this, the data set, the package, is when you go get it, there's this sort of wonderful like machine learning problem that you can go try to tackle. And this is sort of a remix of one of Albert's earlier slides. But the thing to note here is we have this mathematical model that we sort of know and understand. Like the aircraft itself, we want to learn how to subtract that signal off. And so in the parlance of this field, they call that calibration to learn the effects of the aircraft, and compensation to remove the confounders, which is really just training and inference. So you can just substitute that whenever you hear me say calibration is training, compensation is inference. So we have the permanent and the induced and the eddy fields. They're like vector components. If the plane flies over sort of a magnetic mountain, it'll induce like a larger field in the plane, and we can understand that just by looking at the map. Similarly with the eddy field, and the permanent field just rotates with the aircraft. And so we like this sort of explainability component, and we were thinking, how can we keep this in a sort of knowledge-informed pipeline with machine learning? And then we'll let the neural network take care of these transient fields, the communications, radar lights, whatever else is going on in the cabin. And so we thought, we have this Tolles-Lawson model. How can we inject that knowledge sort of like in the same way in 4 different like parts of the pipeline? And the one I'm going to talk about, the one that works best, is keeping it in the architecture itself. And because Julia has flux.params, it turns out you can put things outside of your normal like chain and just train on everything at once. So it's very convenient to try this. This is an example of that. So normally you have your neural network and whatever number of hidden layers you like down here. But up here, this is sort of an explicit representation of that Tolles-Lawson mathematical model, where I can keep the meanings of the permanent, induced, and eddy fields and take a vector norm and subtract off a scalar correction. And so I wanted to test very quickly does this actually help and how? So the way we did this is we have this existing data set. I selected 20 instances of one small line. So there are flights and flight lines, and every flight's made up of multiple lines. So 20 instances of one line, 20 instances of two line, all the way up to 20 instances of 25 lines. And I wanted to see like how quickly can I learn that field that I want to compensate with. And so here we're combining these two techniques at once. And then I'm going to test on 7 held out flight lines. And so what you see here is this is the result for those 200 sort of trained test runs. And each point here is some nanotesla compensation error. So over here, this is training duration in terms of flight time. And so what we want to do is get away with as little flight time as possible, because you have to fly the plane for 12 hours and then compensate. Well, you know, that's maybe not helpful for operations. And so the thing I want to draw your attention to is when you just use a regular neural network and you don't do the informed architecture, things after you add enough hours like sort of settle down. But the place that I was very interested in seeing is early on, if you use this knowledge-informed architecture, with just like less than an hour of data, it seems to hold together better. So when I'm adding to my mathematical model that I already know, then I don't have to use as much data. And I repeated that on several of those other held out flight lines. And it turns out, like, just to prove, like, I didn't just pick the one flight line where this worked on. Sometimes it doesn't help very much, but it doesn't hurt. And sometimes it helps kind of a lot. And so the operational relevance there is that we can calibrate in as little as 30 minutes of data collect. But this knowledge-informed architecture doesn't seem to help beyond a couple hours. The bonus is we get some explainability out of that. So on the left here, you can see in blue the uncompensated magnetometer, and in orange, the actual anomaly map that we were trying to get to so we can do our measurement. You'll notice there's some spikes in it. And if you look at the current for the strobe lights, there are spikes in that. So the lights are turning on and off. It's messing our magnetometer readings. And they exactly overlap there, except for a few spots. There are spikes that weren't on the current. So where do those come from? It turns out when the plane is banking, it's changing its alignment with the Earth's magnetic field. And that changes like the amount that you need to compensate. And so you can see as this plane's making a little turn, there's a spike. Some of that's accounted for by the Toles-Lawson model. But then there are other times that there are spikes in the neural network, and that's accounted for by those strobe lights and things. So we get this bonus in explainability. We need less data. And then in the end, it doesn't always hold up, but that last step, the navigation accuracy, can be better too. And then the thing that we're looking forward to like now is trying to bring some of that into the Kalman filter itself. And a thing Albert did for his dissertation is actually embed the weights of the neural network into the filter states themselves. And then, and you can do this with Toles-Lawson or both. And it turns out when you do that, this was actually from a real data collect we did later on. The two approaches that are working best are the online version and the informed version for the navigation error. And with that, we'll do some demo of the map.
Yeah. All right, so we've been working on creating some demos that we're going to put in the public repo. They're not actually up yet, but they will be very shortly with the next release. And just to give you a little bit of background on how these maps are generated, because they're important for the navigation. And so generally, you start with some sort of GXF file that's kind of a standard map file. And we have this built in MagNav.jl that you can convert that to an H5 file, HDF5, for fast loading and unloading, or I guess saving of the map file. And so this is what the raw map looks like. And then before I mentioned the GeoSurvey aircraft, and so what they actually do is they literally just fly back and forth in these lines. These are flight paths for how they actually collect the data, and then this is compiled into a map by the GeoSurvey company. And then I'm not going to show some steps where we're importing some maps that I've already processed, but overlaid here are 3 different maps. Let's see if I can zoom in. 3 different maps are shown here. One is the NAMAD map. It's a large-scale map And it's not the sun, don't be fooled. And this lower part down here, this is all real data. And what's going on here with these lines, this is all filled in using k nearest neighbors. Basically, the map kind of ends right here. And so just to make the map complete, you have to fill it in. And that's important for doing that upward continuation that I mentioned before. If you have a bunch of zeros in your map using a Fourier transform, it's a big discontinuity and it's not going to perform very well. So you have to fill it in with some values. And then this greenish map here, this is the Eastern Ontario map up by Ottawa. And then this gray map is the one I just showed there. It's the smaller map. We're going to skip this just to give Alan more time. And for that upward continuation, so actually what it does in the function itself, it's kind of fancy. It actually expands the map outward because basically it's collecting, the upward continuation assumes an infinite map. And so what you want to do is expand the map. You don't actually have data, but you can kind of use fake data to help the magnitude of the value be more correct. And it does this fancy thing where it wraps each of the edges, so this side actually matches this side, and top matches the bottom, and it's all meant just to give the most accurate upward continuation.
What's the black line?
Oh, that's just the original map there, and so everything outside of it is filled in. Yeah. So this is the Eastern Ontario map. And now we have this functionality where we can actually combine maps. So I mentioned there was the NAMAD map over here and the Eastern Ontario map here. And so if you're flying around in this Eastern Ontario and suddenly you go over here, you don't want it to just have garbage for the map. So it'd be nice if they're combined and you can smoothly go between the two. And so this is a new functionality that we added to the package, and it's really meant so that you can do it in operation. And then I'm actually going to hand it over to Alan just to give him as much time as possible.
Yeah, we'll try to leave some time for questions too. So this is just an example walkthrough of one of these inform models. It's model 3 in the code if you wanted to look that up. But basically here I'm showing how you can select a flight 1006, which is composed of several lines, perform Toles-Lawson compensation using these lin-comp params, which are also defined in MagNav.jl. This is an example of the field that we're looking for, and then the very noisy uncompensated vector and scalar fields there. So here I'm just selecting one of the little loops that Albert was talking about to do the calibration, and training that model. And here, I set myself the challenge of I want to use a single scalar magnetometer, a single vector magnetometer, and using the same flight, so lines 3 through 6, can I train my inform model using some features for the neural network, which are the currents, and the vector magnetometer and scalar magnetometer readings. And I'm just going to do 100 epochs here, set some fields, and the whole thing trains in like less than 4 seconds. And gives you these outputs. And so you can see how well we're doing here. This is similar to the chart I showed in the slides, but here we can dynamically update. And then also the navigation performance. And then there's a simple function you can call to create that GIF that I was showing you guys earlier, using some of that data. But yeah, the nice thing is we can come here and sort of dynamically change out things. And it'll just work. So if I wanted to add, let's say there's these discrete cosine matrices that sort of tell you which way the plane is banking. So this is just the diagonal of that matrix. And if I hit enter, then you can see it launches, it's training. We can see in just a second if it, so it gets less compensation error because I have more informative features, and it'll run through and you'll see it'll fit better. And yeah, I wanted to leave some time for questions too.
Yeah. And something Alan showed me, I didn't know this before.
Oh, yeah.
There's a nice little docs feature in Pluto. And we have pretty extensive docs for all of our functions and whatnot that, explain everything that's going on. So, yeah, if anybody's interested in trying out these examples, it should be pretty easy to kind of get your hands dirty.
So yeah, we wanted to leave time for questions. Go ahead. I think he's got the mic, so.
Yep, cool. Very neat. Do you think you can sort of reverse this and use your map to come up with a maneuver that would calibrate your model even more quickly?
So they do talk about you need to be able to exercise all the degrees of freedom for like the coefficients in Toles-Lawson. And I imagine as well for like if you have some of these cabin components, you need to be flipping things on and off. You want to pick those up. But yeah, I think the main thing they try to do for that is make sure that they turn. So like the Toles-Lawson the calibration maneuver involves some like roll, pitch, and yaw, which apparently if you're on that flight is not enjoyable. Yeah. But you're right. Like you could probably find regions of the map that would do a better or worse job of exercising those degrees of freedom.
Cool, thanks.
There's two over here. Yeah.
Yeah. So you mentioned upward continuation. I was a little bit confused in the graph where you showed the longitude and latitude, and you're saying continuation, but it looked like you're extending the map in the longitude and latitude. I thought continuation was about altitude.
It is, yeah. And so that's just, that's basically the pre-step for what you would do for upward continuation. So the first thing you do is you expand the map upward or outward, and then you go upward. Yeah. It's just, I'm showing a step along the way, basically.
So if you imagine the field here depends on sources
Everywhere.
out here. Yeah. And so it's easier to go this way and sort of bring everything in than it is to go down because you don't have extra information as you go down, which is why it's unstable. There's one more question in the back.
Hi, yeah, thanks. My old geophysics professor had always told me, or like basically in every lecture said, that the Earth's magnetic field actually changes with time. And so I was wondering, how much of a navigation error do you actually make if you assume it to be constant, as I figured you do here now, versus if you actually had like a live updating magnetic map? And whether this actually depends, let's say, on the region of the world. I don't know, is the Earth's magnetic field changing more quickly around the poles?
Yeah.
Or
So it does change over time. So if I could just go back to the slides here, these different components, the core field is slowly changing over time, and we account for that. There's a very well understood model, like a 13th order harmonic model that accounts for that, and that's super well understood. So that's not an issue. The temporal variations, that's a little bit more tricky if there's like a magnetic storm, that type of thing. Really what you want to do to account for that is you can just measure that on the ground or somewhere in space. You can have a measurement that accounts for that. And the anomaly field itself, what we actually care about, that's what all the maps are the anomaly field. That's pretty static. Like over a decade, it might change by like a nanotesla or two, like a very small magnitude. So it's not an issue.
so looking at the numbers here, you may end up with something like, I don't know, a meter off in your navigation in the end, because you're like several orders of magnitude, your temporal variations are smaller than the other ones. So is that kind of like the scale that we're talking about?
Can you repeat that? I couldn't.
Sorry, I'm just like looking at the numbers here of your nanoteslas.
Yeah.
And whether this basically means that if you assume your Earth magnetic field to be constant, that you end up with like your navigation being like a few meters off, which I guess in
Yeah,
navigation,
if you assume the core field was constant, you'd be way off.
yes, exactly. But like your temporal variations, if they were constant, yeah.
Yeah, the temporal variations can also be accounted for with your navigation filter. You can add some states that account for that, so that's less of an issue.
Is it satellite toolbox.jl that has the IGRF field?
Yeah.
So yeah, there's a Julia package that actually, there's this International Geographic Reference field, I might be getting this wrong, IGRF, that's updated every 5 years. It takes account the large variations that are slow over time. And then there are packages that will let you query latitude, longitude, altitude, time, and then you can pretty much account for that. It's a good operational question. There's one question here.
Are the reported errors in this work magnetic navigation only, or is that INS-fused magnetic navigation?
So the compensation errors are just nanotesla, like we know what the map should be using, say, a GPS signal as a reference, and then we know what we're measuring. So those I don't. You could imagine they're not really INS fused in that sense.
No,
No, but I think he's at, so for the navigation error, yeah, that's always with your INS. You would,
Yes.
it'd be terrible if you just had your magnetic value. Yeah, you need to have some sort of idea with the INS where you are. And I actually made this plot while we were answering questions. So I changed the upward continuation altitude to 10,000 meters. Before it was at 395 meters. And you can see how the features kind of fade away as you go up in altitude. Basically, it's like a low pass filter. So if you're up 10,000 meters away, you're not going to navigate as well just because you don't have as much signal up there.
So I'd assume you really have to fly like a plane through the magnetic field to do this mapping. I mean, like how much does a satellite sort of like sensors can give you sort of like a rough estimate that become a prior if you don't have, if you have areas in which the airplane didn't fly. And that, can that work or?
No.
Yeah,
Short
they're
answer,
too
no.
far away.
So actually, I had this little number pasted here, which is the distance to the ISS. So up in space. So if I run this, it's going to take a minute to run, I think. You'll see it's basically a point. You don't have any information at that altitude. For this field, you still get core field measurements. Like that does change. So you can use that to navigate, but you're talking thousands of meters of error. But the magnetic anomaly field you just can't use at that altitude at all.
Okay, so let's thank the speakers again. Yeah.